Lung Hung from Purdue University. I'm going to tell us about many body physics with cold atoms trapped along nanophotonic resonators.
Okay, first I would like to thank the workshop organizers for inviting me to this to give a talk about this topic. As the only person who's talking about coupling coatoms to nanophotonic resonators today, I know there's some other talks tomorrow. I think I would probably still talk a little bit about some of the measurements to give more credibility. Some of the measurements results I've done when I still have some overlap with the Kimball group. This is and so I'm kind of spin off and come to Purdue to study to propose some experimental schemes to study many biophysics with nanophotonic resonators. Okay, so we've heard wonderful talks about using photon-mediated long-range interactions with coatoms. One approach is a driven cavity approach, that you put your fabric BEC into your fabric cavity. It could be a single mode cavity, it could be a multiple cavity, it could be two cavity modes, and then you dry the BEC with external pump of and these atoms with enough pump power that will resonantly couple into the cavity mode and then induce self-organization. And like Ben said, in this case, you have a lot of atoms, so collective coupling is actually helping you. So although in this kind of system, you still need strong coupling between single atoms with cavities, but cooperativity requirement is not so high because all these atoms kind of collectively couple to the cavity modes. So yesterday we also heard Monica talk about another scenario, is by now fixing all the atoms in space, and then take two of the stable ground state of the atoms, and then we're going to use an external pump to drive a two-photon Raman transition with one of the photon that get coupled into either it's a cavity mode or it's a waveguide mode that I'm going to work on, and then this photon either induce another spin fit in another remote atom, and then that the atom absorb this photon and go back to another ground state. So this way, you can kind of engineer an effective spin system with spin exchange interaction, and also with other schemes you can engineer spin ZZ interaction. But of course, to engineer this kind of spin system is much more challenging because you really require the photon to stay in the cavity or stay in the waveguide to guide the interaction. So the cooperativity parameter is very important, and it typically needs to be much bigger than 1. All right. And so this kind of idea using photons or quantum waves to mediate interaction is not really new to atomic physics systems. For example, using trapped ions, people have been using phonons to mediate this interaction. So they have been able to engineer transparency models, have been seeing very wonderful results like frustrated magnetism or quench dynamics that break locality with long-range interactions. So I'm very interested in doing this kind of experiments. But however, then I would need to search for a system with very high cooperativity. So kind of, we all know that the figure of merit in this cavity QEDs, with especially photons, is that you basically is limited by the square root of so that tells you the number of coherent cycles you can drive spin exchange within the system before the photon is lost for good. All right. So it's ultimately being limited by square root of the cooperativity. And that's limited by basically the quality factor versus Wolfram that everyone knows. So I kind of plot kind of some of the represented systems around the world, and with very impressive demonstrations of this fiber fabric cavity with the cooperativity more than 100. So you could get number of coherent cycles of more than 10. And then Monica has this cavity with the cooperativity 50, and also looks very promising on the plots. So we see that there's still some room here, down here, all right, with very small volume. Mostly it can be done using atom coupled to photonic crystal or resonators. But the challenge is that you really need to make the quality factor as high as all this either free space mirrors or this silica-based optical resonators. All right, and we can also compare. But before I continue on, I would like to compare to some of the very interesting quantum systems that has long-range interaction. For example, dipolar quantum gases, polar molecules, or even optical atoms in lattices. The number of coherent cycles versus loss, I believe it's on the order of a few tens of cycles. Reaction is probably even slightly more higher. The best ones are with coatom systems, probably trap ions. So it's approaching 100. So if we can realize something with similar level, then at least we can study some quantum mechanism with similar fidelity. All right. Going to nanophotonics, first of all, the index guiding and provides and total internal reflection provide very strong confinement. So it helps us to confine photons in the volume that's basically sub-diffraction limits. All right. And so in the closest cavity QED analogy, you can then pattern photonic crystals along your waveguide and make them mirrors, and then make a very small volume, and that's much smaller than lambda cube. Then you can create a very strong single photon Rabi frequency, much bigger than gigahertz with co-atoms. All right. But I think nanophotonic system can do much more than simply just squeeze the volume. It can also be used to engineer basically the photonic transport probability of photon that can give rise to many more unexpected properties. For example, going into one dimension. Okay, so now instead of a single mode or multi-mode cavity, now let's make a waveguide. So here we use basically index modulation along the waveguide. They can create a photonic crystal. So this index modulation is basically scatter photons like ions scatter electrons in solids, and therefore they can create band gaps and band structures, right? And so if we align the atomic resonance frequency very near the edge of the band, okay, so here you get the so-called Fan-Hole singularity that would increase the photonic density state. As a result, the coupling strength, so which we call gamma 1D, which Anna introduced, the coupling for a single excited atom into the photonic channel can be greatly enhanced. And in some of the cases that initial study, we can make it much bigger than the decay rate into free space. Okay. So what's even more interesting is when you align the atomic resonance frequency not with the band, but inside the band gap. In this case, there's simply no real photonic modes for photons to propagate. And so in this case, a single atom, if you excite it, it would want to so single excited atom would like to emit the photon into the waveguide, but there's no way it can. So what it can do is off-resonantly coupled to the waveguide mode. And because it's off-resonantly coupled to the modes at the band edge, it can couple to multiple modes at the band edge. And if you sum up the multiple modes at the band edge, the summation of this wave function becomes exponential decay, because this is in 1D. All right. And so the length scale of this photonic wave function depends on square root of A, the curvature of the band, and also the detuning of the time frequency near the band edge. All right. So basically, this ratio determines how many number of modes you couple. So you can kind of think this is an idea by Derek Chan and his co-workers that basically you can treat a single atom, excited atom, as a cavity that traps photons, and this is a multi-mode cavity, and therefore it's summed up with a finite length scale. So if you trap an array of atoms along this waveguide and treat it like spins, they would require coherent spin-spin interactions, where the interaction strengths are basically determined by all the summation of all the modes that can off-resonantly couple to the atoms, and with some sign changing functions based on the localization of the atoms. All right. Going into 2 dimensions, we can also find very similar analogy. So with a very simple 2 square lattice with atoms trapped along the lattice, we can actually engineer also a quasi-band gap where we can align the timing resonant frequency inside this quasi-band gap and very close to the edge of the band. Now there's also very strong resonant coupling to the band edge. But what is different is that now we've got a 2-dimensional Brillouin zone. So we are coupling to 4 edges of the Brillouin zone. In this case, particularly, it's at the x points. All right. So when an excited atom wants to emit, it will emit into basically either this pair or this pair. Okay. And so it's kind of a Cavity QED, like February Cavity analog, is a 2 orthogonal cavity, right? But however, this is a multi-mode, all right? So if you look at the coupling strength to different K factors in this photonic band gap, where here I'm plotting inverse of the effective mode length that tells you the strength, then you can see that this coupling is very anisotropic, and at the same time, well, it extends over a lot of modes in one direction, small amount of modes in the other direction. So the sum up of the effective interaction is, just like a star shape, all right? So if we, and then because of this multiple number of modes all coupled to the atom, so you can calculate the effective range of this interaction. And in 2 dimensions, it kind of dies off like a little instantly. Right? So if we would like to, if we use this as a effective 2 cavity, and then we couple a BEC to this 2-dimensional photonic modes, then you would kind of form very interesting interaction strength, this star-shaped thing, which I don't know how to calculate. Maybe some of you will have some idea. And then we can see organization of the atoms. And we can also try to collect light that's leaking out into the photonic band and using, for example, photodetectors to look at it. Right. Or we can also again use atoms to engineer speed models, and use 2 photon Raman ponds, and then we can engineer a spin-spin interactions using this 2D photon system. Okay. All right. So I want to emphasize that using nanophotonic structures give us a new opportunity, basically, to engineer the underlying photonic, the transport quality of the underlying photonics. So it could be used to induce long-range spin-spin interactions with dimensionality, either 1D or 2D, and different topology. For example, I'm discussing about square lattice here, but I can engineer a hexagonal lattice, and effectively it's a 3-pair cavity, multi-mode cavity, or something even more exotic. All right. So with this, then at Caltech, back at Caltech, we have engineered basically a silicon chip with silicon nitride structures across free space windows. Then we can send laser lights through it, and then direct laser cool atoms on the chip, okay, using a mini optical trap. And then our hope is, well, okay, automatically we can trap atoms along the structure. But how do we do that? Okay, so the product we have first delivered was the so-called aggregated photonic crystal waveguide, which consists of about 150 unit cells of this periodic modulated kind of Bragg gradient photonic crystal. And we have designed trap mode such that we can trap atoms inside this photonic crystal, and at the same time can be very strongly probed by the guided mode. Well, of course, then we realized that the simplest way to trap atoms along this crystal is by directly shine the laser beam from the top of the crystal. There will be very strong, well, some amount of surface reflection of the dielectric structure, and then form interference pattern. So you can use this as a trap to trap single atoms, well, multiple atoms along the structure. And then you then send light through this structure, look at the transmission spectrum. You can see that with just very typical MOT, we can see that there is a pretty strong, about 70% of transmission with trapped atoms along the crystal. To really see that this is really strong, each of the atom has very strong coupling with the alligator waveguide, then we can measure the decay rate near the waveguide. And we see that when we load almost like a very small amount of average number of atoms on waveguide, on average there's only one single atom probed at one time, then we can see that the decay rate is about 2 times the decay rate in free space. And when we increase the average number of atoms surrounding the waveguide, we start to see that more and the decay rate becomes faster and faster. This kind of dependence going from one atom decay to decay rate that's dependent on the number of atoms around the waveguide prove that there's a very strong coupling between single atoms along the waveguide. And we can further tune the atomic resonance frequency near the band edge, but crossing the band, or make it inside the band gap. And by doing so, then you can basically control the size of the collective, the size of the dissipation rate into the waveguide mode, or the coherent interaction between the atoms. And so by looking at the absorption spectrum, and in particular looking at the dispersion line shape, you can extract the so-called collective decay rate, which is this red Longrange-like peak, and cooperative level shape, which is a dispersive-like shape here. And deep in the photonic bandgap region, then you can see that this decay rate is strongly suppressed, whereas the dispersive shape, still remains. So by placing the photonic band edge, by placing atomic resonance frequency inside the band gap, this is where you can kill mostly the dissipation, and that the atom trapped along a photonic crystal evolve mostly based on coherent evolution. Okay. So with this, then let's estimate, like when we place the atom inside the band gap, what would be the cooperativity of the atom-photon cavity along the photonic crystal. And it turns out it's pretty much down here. All right. The reason is because the quality factor that we have fabricated is about 10,000. So there's no hiding. This is where we are here. The atom-induced cavity length with this kind of parameter is on the order of 15 micron. So whereas the atoms that's being trapped along the photonic crystal has a spread of about, I think it's about 5 micron or so. So basically the atom-photon cavity completely covers the entire atom chain, which only consists of 3 atoms. So therefore the interaction between the atoms is still kind of mean field-like, so you can kind of extract all this parameter collectively as just NJ. All right. And what is plotted here for comparison is another very impressive demonstration in looking group here. The quality factor is very similar, so therefore we landed on very similar spots. Okay. So how do we improve this? Of course, going to a quality factor of the median is a possibility. This is not completely undoable, but it could be technically very challenging. Another thing is, because we are using basically block gradient is basically index guiding waveguides. So if we can adopt other design to achieve even flatter bands, so that means the band hole singularity will be even stronger near the band edge. So we would be able to further increase the interaction. And one last result is to reduce free space emission. For example, what we can do is by a brute force ways is loading the atom into the photonic crystal, hiding them from free space. Therefore, the emission rate can be reduced. Or we can prepare the atoms in the selective radiant state, like Alan just talked about, and that's another possible way of increase the the fidelity. All right. So up to this point, we're realistically here. But to be honest, there's still some room, quite some room here that we may be able to explore with resonators, nanophotonic resonators. In fact, actually, in this region, it's more like micro resonators. One of the possibility is that just engineer a very simple linear waveguide. So now give it a photonic crystal. Very simple waveguide enclosed by Rock gradient mirrors. This could form a pretty nice cavity with a quality factor about a median that has been observed. All right. So this would be a backup plan, of course. Another possibility is, there's now a huge industries of trying to make very good silicon microring resonators. This is mostly for frequency low generations. So all this microring resonator is basically probably the simplest resonator that you can expect for this kind of lithographically patterned structure sitting on directly on the substrate. The record intrinsic Q can reach about 50 million. That's actually being fabricated. The expected limit in the telecommunication band is more than 100 million. So this is something very interesting. But of course, we need to redesign it for Q over V optimization. So if we can trap an array of atoms along these crystals, along these wave resonators, then there might be a way that we can perform some spin experiment, quantum magnetism experiment here. I'm personally now pretty much drawn to this one because these ring resonators actually have very interesting linear and nonlinear quantum physics, quantum optics with it. One thing is you can put a bunch of ring resonators together, make it a couple ring resonator array. Because the way the photons can hop between resonators is pretty much dependent on the circulation, you can actually engineer some differential path lengths between photons that hop from this side to this side and this side to this side. And as a result, you can actually introduce geometrical phases based on your design. And so this kind of couple ring resonator then can be used to engineer some topological lattice models that has been widely discussed in quantum physics, and in particular, Harvard's group at JQI have been realizing many of the interesting physics here. Another thing is on the ring resonators, these waveguide modes are traveling waves. Okay, and because of high confinement, all right. So in the free space region where you have evanescent waves, there's substantial axial component that's 90 degree out of phase compared to the electric field that you initially thought you launch into the waveguide. So what is plotted here is when the light propagates along the waveguide, following this gray line, gray arrow here, the electric field factor actually propagate like this, electric field factor actually rotating like this. So that means the line mode in here is chiral, and if you define quantization axis, I can say that on top of the waveguide, the light field here is sigma plus. But by time reversal symmetry, for a waveguide mode that's launched in the opposite direction, then the electric field orientation becomes sigma minus. So there's this chiral, very strong chiral propagation of waveguide modes. And if you couple a quantum meter that has internal structures that couple to different polarizations with different strengths, then you can observe some very interesting type of quantum optics and even introduce non-reciprocal transport. All right. The last one is that all these couple ring resonators, if we can load atoms onto these rings, then you can kind of think of it as a realization of many proposal couple ring resonator arrays that can be used to simulate some condensed matter. So we now fabricate many ring resonators. I talk about, so these are array of resonators coupled to the waveguide bus, but currently we would and it's sitting on top of a transparent membrane. The membrane would look like this. It can fully transparent transmit light so that we can direct perform laser cooling on top of the ring membrane. And at this moment, we only want to concentrate on coupling atoms to single resonators. Okay, and the membrane will be designed to host whatever structure that can be used to trap atoms very tightly above any resonator we are interested in. For example, in this case, we have the two lines of side scatters near this red track resonators. So we have tuned all the thickness of waveguide as well as the distance of these side structures, such that if we shine a laser light from top of the membrane, we can create a very, very strong and tight trap right above the waveguide. How close is it? It can be closer than 100 nanometer. But we also have to consider surface cosmic polar interaction. So in fact, eventually we don't have infinite amount of laser power, and also we don't want to create super large light shift. So this is where we limit ourselves at about 100 nanometer above waveguide, and so we can still create a pretty stable trap. And with this, the effective mode area that an atom sees with a propagating waveguide mode is about 3 to 2 microns squared. Okay. With so many waveguides along the waveguide, resonators along the waveguide path, and the way we can characterize the optical probability in the waveguide is to use basically a CZ camera to collect the light coming from waveguide when we scan the frequency across the resonances. And we can just zoom in and look at one of the waveguide and look at its intensity, and then we can fit the line width. At this moment, what we got is not very impressive. It's about 35,000, the quality factor, which project to a productivity on the order of 1. We scratch our head, why is it like that? Why am I not getting 1 million? So it turns out that the reason is because we were too greedy. We kind of designed the waveguide structure to minimize the mole area, but forgot that this waveguide bends, so we don't provide enough index guiding, so this light will just lost into the substrate. So what we did is we consider all this bending loss, also consider a limit of actual fabrication loss, okay, and then which we put in about at 100 million, and then we can run the optimization again. So now we get some more realistic estimate and much better height and width, and with a projected cooperativity parameter as fast as 600, assuming that we can achieve fabrication losses with quality factor 100 million. So I would pretty much like to put another updated figure here, but this is just some very new data here. But let's be realistic. Even if we could be achieving 100 million, we could be achieving 10 million, we could be only achieving 1 million. But with anyhow, it's kind of to my surprise that, so let me see how atoms can interact with the waveguide mode, even if I only have a quality factor of 10 to the 5. It turns out that just with this single atom presence, okay, and then you put the waveguide to be critically coupled to the waveguide bus. Normally, if there's no atom present, there will be no transmission because of the resonance of the waveguide. But with 1 to 10 atoms collective coupled to the waveguide mode, they can completely destroy the cavity resonance and then make the waveguide transmit again. If you apply, and because this is the propagation is chiral, and then if you apply put an atom with internal structure and then apply a large Zeeman shift such that you ship away the resonance for sigma plus and sigma minus, then you can create a situation where if you send in a light probably into the right, you see this kind of transmission spectrum. send light probably into a lab, you see a shifted transmission spectrum. So if you put the laser frequency right at this atomic resonance here, then if you send light to the right, you have transmission 80%. If you send light to the left, there's almost no transmission. So this is a very interesting non-reciprocal light transport. And if we even improve the quality factor even better, then this transmission can be as strong as almost 100% with only 10 atoms coupled to the waveguide. Okay. So I talk about the structure that we have been trying to fabricate at this moment. So the vacuum system that we have already constructed will consist of basically a chip stage that we can easily put into a low lock chamber without breaking vacuum. We're going to have a microscope objective to address single atoms along the waveguide, and then we would have co-atoms being pushed into the center of the chamber so that we can always keep this part freed of alpha atoms that we used to couple to. And this is some kind of side view of this optical chip, and we trap atoms outside of the chip. So this is a better view, viewing from the top of the viewport. And then now we have achieved about from 10,000 to 10 million trap atoms transporting into the window with dominant chip, which doesn't have any structure in it, just window. And then light, addressing light being sent through a high numerical objective, and we trap an array of atoms, and this is the CCD image which is collected through the same objective. And so eventually we are going to overlap our array of atoms with this waveguides, and then trap them and do the experiment. Currently, of course, this loading is done with free space. There's no structure in it. But with free space loading with this tweezers, actually the loading is highly efficient. With only like 1,000 to 10,000 background atoms, we can load already about 3 to 5 atoms in each of the trap. So these traps are not collisional blockade limited. But once we load this trap onto the waveguide, we respect collisional blockade. We limit the number of atoms within each trap to be 0 or 1. And also with the way with this narrow structure present, we expect fully different loading dynamics. So it's certainly not going to be as easy as what we've been doing in free space. Last one is if we want to load a defect-free lattice, then we have to perform some schemes. For example, something that's recently developed here at Harvard or Bowers Group or Readers Group at GLO. Okay. So I've been talking about a lot of advantages going with photonic crystals and then inducing interaction, finite range interaction. And now if I go to resonator modes, again, I'm going back to this infinite range interaction because we are just coupling to single modes, right? So what's so interesting about it? Like Monica mentioned yesterday, well, we can apply some trick. So now that if we have very good cooperativity, then we can allow to use something. For example, this is some scheme that's developed actually in ultra-cold atoms and optical lattices. What we're going to do is that we are going to apply a uniform, say, gradient, ground state energy gradient, or like locally address the atoms with a different potential energy, so that we can shift the ground state energy, in particular this S state here, differently according to the localization of the atoms. All right. So originally the Raman transition. So if an atom at psi I solve the Raman pump and then emit the photon into the waveguide, all other atoms along the waveguide cannot absorb this photon and pair with the original Raman pump because energy conservation wouldn't allow it. But this transition can be reinstated by putting a different frequency component in the Raman pump that with frequency matches the shift between the two atoms. Okay, so with this way, then we can basically reintroduce interaction between atom pairs, individual atom pairs, one by matching all the frequency component in the Raman pump with the individual pair of atoms that we want to create interaction with. So with this way, then we can simply just spectrally engineer the Raman pump, or even simpler is by shaking the Raman pump or modulating the intensity of Raman pump with different frequencies that we can create basically arbitrary pairwise interaction between trapped atoms. Okay. And we can also put in different schemes to control not only just spin exchange interaction, but independently control XX and Y interaction. And this is the actual scheme for using atomic season to create this spin model. And so basically all these dynamics can be fully engineered just by a single or multiple Raman pump, depending on how you want to your spin model to look like. And the dynamics can be frozen by suddenly remove the Raman pump, and then we can start to look at the spin state of the atoms. So this is a way for spin state detection. Okay, and this kind of thing is actually it's basically a Fourier driving of this of the coupled system. So actually there's actually some errors in it, but there's also some schemes that we can remove this error. All right. So one of the first experiments that we are interested in trying is to use an array of spins and engineer basically a simplest model you can think of with long-range interaction, but exactly solvable, which is this Helden-Shastry spin chain with boundary condition and 1/2 square dependence. Okay, this is the pump power requirements that we have calculated to induce this spin change, and also the overlap with the exact solution. Okay. Another thing is that, well, with this chain of atoms, we can even engineer something more complicated. For example, like a later lattice model. Here I'm marking the radar atoms with different colors, but in fact they are just all the same atoms, and also the energy gradient is still the same. It's a linear gradient. But we are going to use Raman pumps with different directions, okay? And so there will be phase difference between these different atoms at different colors. So, and then we can map this into a ladder. And by controlling this, the spectral components in this Raman pump and the phase difference between them, then we can engineer basically a ladder with a diagonal tunnel element, and also even a phase shift between the tunnel. And this is a simplest model. They can exhibit a flat band and also non-zero flux, magnetic flux through the lattice. So this is the simplest model. They can give us interesting topological physics with a simple array function. And of course, if we, for much longer term, then we can probably even drive this with two-dimensional crystal and then engineer a Helden model. And because we're dealing with Huckel boson, this model is immediately strongly interacting. All right, so the ground state of this kind of model is should exhibit fractional statistics. By further introducing long-range ZZ interactions, there will be other solid, supersolid phases that can appear in this phase diagram. Anyway, so a kind of list of the possible things that we can explore with this kind of system, if you believe that we can do that. Another thing is with this large transparent membrane, basically it would allow us to pattern whatever nanostructures on this membrane. For example, we can pattern structures with subworking distance between the structures, and therefore by loading atoms near the structures, that using cosmic polar attraction, actually we can create periodic lattice potentials that can break beyond the limit using free space lasers, and we can go to length scales like sub 100 nanometer length scale, and greatly increase the interaction energy of co-atoms to up to megahertz or even better. Right. So with this, I would like to thank my crew members. So the verification is mostly done by Zuhan Chang, a graduate student, and the atomic physics part is done by postdoc making, and also my another graduate student, Brian. And additional thanks to Jeff Kimball and other dear collaborators. Thank you.
We have some questions.
Yes.
In the plot where you've shown the dispersive and the dissipative components on the atoms near the band edge,
Yeah.
how can one distinguish the signal you're seeing from like a signal from a single cavity mode? Because if I look at that plot, it looks fairly similar to what I would see with a single cavity mode.
Well, I kind of jumped the slide because I'm already away from the group, but you can actually take ratio between the coherent interaction and the dissipative part. You actually see exponential suppression. It's better than 1 over delta. 1 over delta is typically what you would expect by the suppression by single cavity. So this 1 over this exponential suppression is really due to band gap physics instead of single mode.
So I have a question about the difficulties of having the atoms near the surface of this thing, and whether you have to worry about the various decoherence things just coming from
Heat.
yeah.
So how do I comment that?
Yeah, I mean, how bad is it?
So at this moment, the only experiment that's being performed with atoms trapped near the nanophotonic structure is Kimball group and Looking group, and there hasn't been such many minutes. So I really cannot comment on that. But what I can comment with is, so to use photons to mediate this spin exchange interaction sounds to be much more difficult and more demanding. But if you use use photons like you pump photons in and then that atom is self-organized, this kind of experiment is less demanding on cooperativity. And so of course the time scale will increase. So but the other things is less demanding. So I don't know. It's really like there's two possibilities and you just have to try it. Yeah.
Cool. Yes.
You discussed about creating flutter bands. Do you know which are the design tricks of the photon crystals for creating flutter bands in 1D and 2D?
So index contrast is not a good idea in terms of creating flutter bands. So you want to actually put, for example, say for 1D, then a line defect waveguide inside a photonic bandgap crystal, then you can create a much better band. And so there's other new papers coming out show that the band can be 10 times better. Yeah.
I thank Chen Lung one more time.